In this video we'll start talking about double slit interference, and then we'll talk about some other interference patterns we can have. So what we have is essentially a wall here, and I have a source of waves on the left side of this wall. But what I have is I only have two slots, and they're separated by a distance d, which is this between the center of the slots, and that's the only way that this wave can get to the right of this blocking wall. And then so the waves that get through, they at any point out on this right side, they will either so they come from this and this now. Anywhere over here, they will either constructively or destructively interfere at some point. If they result in totally in phase and they add up together, they will constructively interfere. If they totally are out of phase, so one's at a peak, one's in a valley, then they will totally destructive interfere and it'll be dark. And essentially that results from just the distance. So this is a wave. These are waves moving, and when they hit, they are going together, then they're going to constructively interfere. So, and that happens when the difference in the distance is a wavelength, is a integer number of wavelengths. So in the center, they have to go the same distance to get there, and so therefore they will be in phase when they hit that center point, and it'll be bright. If I go to a point here, which is one wavelength over d, separated as far as sine of theta, or then what will happen is that this one will travel less distance than that one, but when they finally get to this point right here, they'll be in phase, and it'll be bright, because this one had to travel one wavelength longer than that one. And the pattern here continues as shown. And so if one did the trig, one would see that this is the relationship to where I'd find points which are in phase when they get there. It's d, which is the center distance between the slots, times the sine of theta bright, where theta is measured from the 0 up to this point, equals m, or m is any integer, times the wavelength. And if one solved for theta bright, you could just get the inverse sine of any integer times the wavelength over d, the distance between the slots. So you can see this is not to scale, because the smaller the d, if you want to have these spread out, you make d be small. And then for dark is the values in between the integers. So they're the half of wavelengths, or 3 wavelengths over 2 values of the dark. Now also, you don't necessarily, this is done with this wall here and one singular source coming. You could also get this sort of pattern if I had two coherent sources, both at d. So coherent means that they have the same frequency and they have a fixed phase relationship. For example, if I had two speakers both in phase at the exact same frequency, going at one frequency right here, and they're sending a signal out, it'd be loud and then quiet, and then loud and then quiet. Now there's another way to get a pattern very similar to that, would be diffraction grading. This one has, instead of just 2 openings, it has lots of openings. Again, these openings are separated by a distance d, and what diffraction grading that has more than 2 slots kind of has a very similar pattern. All it is you do the same equations you'd use. It's just that the brighter spots are actually more concentrated, narrower, and brighter, and so that's what a diffraction grading give you. Now looking at a single thin slot, or an interference pattern from a single disk. In this case, I have my source over on my right, and my signal's going and I have just a single thin slot of width d, and now what comes from this edge compared to what that edge is will interfere. And essentially, if you did the trig, you kind of see the same kind of, you could solve for it and understand when they constructively or destructively interfere. As you'd expect, at the center again it's bright, But this time, if one did the trig, you find, and theta is still measured the same way from the center. But this time, if you did the trig, you'd find out that at an integer number of wavelengths over this width of the slot, it's now a dark region. So so this is the equation for single thin slit one. So d, the width of the slot, sine of theta, now this theta dark, and equals m, but m no longer 0, because we know when m is 0, that's at the center, and the center is, we know the center is bright. So this m is only one integer numbers, not excluding 0. So 1, 2, 3, and so on, times the wavelength. So if I solve for theta dark, that's the inverse sine of m, this m that doesn't include 0, times the wavelength over d. And again, once again, you can see that I need the thinner the width of this single slot, the more it spreads out. So if you just have these equations, you always have to remember, I mean, they look very similar, but two things are different. For double slits or diffraction grating, this theta, this integer number of wavelengths, gives me bright, and for a single slit, this integer number of wavelengths, so here's a bright here at 1 wavelength over d, and here is a dark at 1 wavelength over d. So therefore this is theta dark, but in both cases the center is bright.